Hi everyone. So the title of this talk is Erlang in Production. I wish I'd known that when I started, or this is nothing like it was on the brochure. First of all, a quick introduction to who I am and why I feel I've got any business talking about this stuff. I work for a company called M5 Networks. The main company is based in New York, but we've got a development and operations office here in Canberra, just down the road in Braddon actually. Our company is about selling enterprise-grade voice over IP. So the elevator pitch goes something like this. You're a business with 50 or 100 people. You want a great phone system with all the flashy features, conferencing, park, pick up, music on hold, ability to transfer and stuff. And there's a feature I keep forgetting, call recording and so forth. But you don't want to shell out 50 grand for a Cisco call manager. You don't want to shell out for a guy to maintain it. You don't want to have to manage the SIP trunking and so forth with the main SIP providers to actually connect you to the public telephone network. So you come to us, and we have a Cisco call manager equivalent. It's not actually Cisco, it's the bit of software that I work on, sitting in a colo somewhere. You lease a line to that, you plug all your phones in, we manage the configuration, we manage the deals with the SIP trunking providers, and because we buy in bulk get presumably better prices, and you just have a phone system that just works and you don't have to think about it. Our system itself, the machines I talked about, run something on the order of 8,000 to 9,000 endpoints. So this is on a single machine. An endpoint is a fancy way of saying a telephone. They run 150 calls per minute at peak load, maybe a little bit more, depends on the day, depends on how many emergencies are happening. We provide features like real-time call control, real-time call recording, so you have a little app sitting on your desktop and you can, if you're the receptionist, you can see who's on the phone, you can see who they're on the phone to. You can do things like barge and whisper, which mean that you can sort of interrupt someone else's call while they're still on the call, maybe do coaching so that you're speaking, only they can hear you, the customer can't. And one of the big things about running a telephone system is that people are used to having Windows crash on them, they're used to having their email not working for an hour at a time or whatever, but no one's used to having their phone not work. They expect to pick up, they expect to get a dial tone, and they expect to be able to make calls 24/7 all the time. So robustness and uptime is a really big part of our business. And our customers get very unhappy very quickly if there's even a short bit of unscheduled downtime. So that's the kind of environment where we work in. Whoops. So what's Erlang? How many people here have actually coded Erlang? Okay, a few of you. This talk isn't really meant to be an introduction to Erlang. There's a bunch of really good basic Erlang tutorials on the web. If you're interested, I'd encourage you to read them. And as was mentioned in the keynote, Erlang is one of these languages that's not the kind of thing you're probably used to. It's a little bit different. It makes you think in a slightly different way. And it's really, honestly, it's worth learning for a bunch of reasons. It's got a nice, simple, powerful syntax. I'll explore each of these in a little bit more detail. It's highly concurrent. It means you can do a whole bunch of stuff in parallel easily in the code. It's highly robust. Crashes are isolated rather than bringing down your whole system in one hit. It's got hot code loading, which is an awesome feature which I'll get into later. We love it at our company, but the thing is, after using it for 4 years, we've kind of stumbled across a whole pile of speed bumps that have made us go, oh, damn, that's not quite what it was supposed to be like. It was supposed to be completely awesome and have no problems at all. Of course it doesn't. But I want to help you guys love it by pointing out these things and telling you how to get around them before you hit them and before they cause you problems. So the syntax, simple syntax. Got very powerful things like list comprehensions. That's a really neat way of doing the loop. This is QSort implemented in Erlang. You can see it's very little code. It's completely type independent, so Erlang's a dynamically typed language. You can pass anything into here and it will sort them. All its types have a strict ordering, so strings will be sorted with respect to integers, with respect to lists and so forth. It's all defined as a strict order, so you can pass anything in your list and this will quick sort it. List comprehensions, simple list management, adding lists to other lists. It's highly concurrent. You can, if you're writing a C program and you want to fire up, and you want to say manage 8,000 phones, as we do, your first impulse might be to just spawn 8,000 threads, and that's going to get you in a lot of trouble very quickly, because the overhead of spawning a thread in C is big. It's got a fixed stack size for a start of starting at 64K up to 2 meg, depending on how your system's configured. And the cost of context switching between those threads can be quite high as you spawn more and more threads. The operating system cost of switching between threads becomes quite high. Your context switch time becomes long, and your performance actually decreases quite rapidly as you get into high numbers of threads. Erlang, because it only runs one operating system thread per CPU, then has very lightweight threads. If any of you went to the Go talk, they're similar in nature to those. And they'll cost you 1.2 kilobytes each. The stack is dynamically allocated as required. And you can spawn... I run a load testing program on my laptop that spawns something on the order of 15,000 threads. This laptop doesn't break a sweat doing it. And you can spawn a lot more than that as required. Concurrency is very intrinsic to the language, so you've got primitives for sending messages from one process to another and for receiving it. Again, a little bit like the Go talk earlier. So here we spawn a new process. We say we want to run in this module the function f with no arguments, and that'll fire up a new... They're called processes in Erlang, which is a really confusing bit of naming, because obviously processes is also what you use to describe OS level processes. Whenever I say process, think thread, if that makes it easier. Fire up a new process running the f function, and that will go into a blocking receive call. Then in our main code here, we say to that PID that we just created, send this message, exclamation mark is your send function. Send a message which is a tuple containing the atom message and some arbitrary data. And then here we receive the atom message, store that arbitrary data in M, and print it out to the console. A contrived example, completely useless, but that gives you an example of how simple and how built-in the concurrency model is in Erlang. It's highly robust. In our system, as I mentioned, we have 8,000 phones, all with a TCP connection to a single Unix process. And our current system is written in C++. If one of those users goes down some path on their phone menu that's not very well trodden and not very well tested, for example, of course we test everything brilliantly, so there's no bugs, but if, for example, there were to be a bug, and we accidentally dereference a null pointer, whoops, boom, seg fault, 8,000 phones lose their connection, 8,000 customers call our support line, and everyone is very unhappy until it restarts. Sure, you can restart it very quickly, the phones will come back up, but as I said before, people don't expect their phones to crash, because that's just not a thing that used to happen, and so they consider it a step backwards if it suddenly starts happening. In Erlang, because each of those phones, if you design your system right, is connected to a separate process, lightweight process thread, and because it's a high-level language running in a VM, if that goes down an unusual bit of code, crashes because you've made a mistake in your programming, which all of us do, it'll crash in that thread, that phone will disconnect, reboot, reconnect, and 7,999 people won't know that anything happened. And that's a really, really, really big win in our environment. And it's got a built-in restart recovery system, so if you design your program right, all of that will happen without anyone having to interfere or anything, and it's great. And as I say, compare that with C++, where if you crash, you're pretty much boned. Hot code loading. I'll get to this one a little bit later, but in short, it means that you can push out changes into a running production system with literally zero downtime. So if you've got a bug, let's say we accidentally misspelled the word conference on our conference module, and when people go into the conference menu, they say, conference, what the hell? We can push out a fix to that without bringing down the system at all, in theory, once we build this hypothetical system. And everyone on a conference will continue to use the old code until they've finished, and then the next time they go into this conference code, it will load up the new module. Conference will be spelt right. No one will have even lost the TCP connection. Their phone stays up. We fix the bug. Everyone's happy. So how did we come to Erlang? At LCA in 2007, my colleague Sam went to an excellent introduction to Erlang talk. Came back to me and said, dude, this is the way of the future. We've got to redo everything in Erlang. It's perfect for us. Whatever. I've got a lot of C++ to debug. Something's causing a null pointer exception again. So he, as a proof of concept, hacked together a TFTP server, which is something that the Cisco phones we deal with talk TFTP. But they talk a really interesting interpretation of TFTP, which doesn't work particularly well with the standard TFTP servers you might download. So he hacked together a slightly modified one that spoke this interesting dialect. and ran that on Erlang. And that was great, and it worked really well. And I'm like, oh yeah, that's kind of interesting, but look, I'm really dealing with a lot of C++ stuff here, trying to debug it still. So I had together a soft phone, and this is where it got really interesting. If we're trying to test 8,000 phones against a system, load test it, so that we know that when we push it out into production, all 8,000 phones will work, and if the system won't just fall over, you've got basically two options. You can buy 8,000 phones and hire 8,000 QA people and have them mash buttons until something crashes, which is not a really good idea. Or you can write a bit of software that pretends to be 8,000 phones and hammers the server and see what happens. And this goes back to Erlang's concurrency thing. I can spawn all 8,000 phones on my laptop and fire them at a server and see what happens. And this is where everyone, including myself, really started to pay attention to Erlang. That, hey, actually, maybe there is something to this after all. And as we've progressed and added new features to the existing call manager, when I say call manager, by the way, I'm talking about a thing that's like Asterisk or like Cisco call manager, but it's our own in-house one. It's now the backbone of our call tracking, billing, and what I haven't written there is also our call recording system. And we're now in the process of rewriting the whole thing because our old call manager is 10 years old. It's suffered from 3 management changes, 18 different changes in direction of the company, and 1 billion people asking for different and internally contradictory features. So Bitmod is set in a fairly solid way, and it looked like a good opportunity to rewrite it with all these great things I'm talking about. And Sam reminded me the other day that we're also writing a new build system in Erlang because Make, for all its excellent heritage, has a few fairly interesting shortcomings, and particularly when it comes to building Erlang, it's I won't go into the details, but it's got some interesting problems that are really, really difficult to solve in Make or nigh on impossible in a couple of cases. So just as a week-long project, we've written a new build system based in Erlang, which is highly parallel and kind of solves all these problems for us. So what am I going to be talking about? Basically stuff we wish we'd known when we set out on this Erlang thing. The VM can crash. VMs give you this great sense of, runtime environments give you this great sense of security. It's like, oh, well, my code might crash, but at least it'll be isolated and so forth. Think Java, you can isolate crashes in that as well, albeit to a slightly lesser extent. Except that that's not entirely true, and there are great ways to very easily crash the whole VM and bring down those 8,000 phones, just like I was talking about before, and make everyone very unhappy. So I'll talk about how you can do that and how you can avoid it. Message queues between processes, you remember that slide where I had the concurrency example where one process is sending a message to another one. That message queue system is really, really simple. Every process, just if it's talking to a different process, they all go into one message queue for that, and it just pulls things off that message queue. And that's great, and it's got some very powerful features, but it can also get you into a lot of trouble. 99% of the time it won't, but I'll show you when it can and how to avoid that. Erlang has a heritage that comes from the embedded world, which I'll talk about in detail a bit more later. But so running it as a Unix-style service, think Apache, where you go service Apache start, service Apache stop, service Apache status. That stuff is actually surprisingly difficult to implement in Erlang, for reasons I'll talk about. Hot code loading, I keep promising to talk about this, I will get to it. It's interesting and not nearly as user-friendly as you might hope. System monitoring is really, 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 really important. Anyone who runs a big system kind of knows this intuitively, but it's a thing that's very easy to overlook, and I'll talk about some really simple places that you can look at the system to monitor stuff that can often go wrong. The OTP is an architectural set of code which comes along with Erlang. It stands for the Open Telephony Platform, and it's all about robustness and building big systems in a way where they'll all hang together properly instead of coding at a low level and solving the same problems over and over again. So look at that, and I'll talk really, really briefly about Dialyzer, which is super awesome and is a talk in itself, but I don't have time to give a talk to that in myself. So how do we crash the VM? There's basically two ways. You can run it out of memory, and that's surprisingly easy to do. Or you can use LinkedIn drivers or NIFs, natively implemented functions. I'm not going to talk about these very much because there's big warnings all over the man pages for when you write this. These are ways to interface your Erlang code with native C code, call out to drivers, whatever, and anything you want to happen really fast. You can do it, but because it runs straight in the same context as the VM, if your code crashes, the whole VM crashes. But there's big warnings plastered all over the documentation about those, so I'm not going to go into a great deal of detail about that. If you start writing native code in the context of a VM and it crashes, well, you were warned. First way to run yourself out of memory is to write non-tail recursive main loops. So who here is familiar with the notion of tail recursion? Okay, good. So you know what I'm talking about here. Here's your main loop. You do something, you wait for some input, and you loop around again. This is how you implement a loop this is one way to implement a loop in a functional language. And the compiler looks at this and says, great, I don't need this stack anymore. I can just reuse the same stack and go back again. And that can lose you a little bit of stack trace information if something does crash, but in general, it's quite efficient. It means this can loop infinitely without your stack growing. Great, that's good. That won't cause you any problems. This is bad. Oops. Added a return value there. Looks pretty innocuous. I mean, if we ever do happen to exit, if there's an exit case somewhere, we'll just return OK, no problem. Except that it has to remember that it's returning OK from each single time this is called, and that grows your stack and grows your stack and grows your stack, and eventually you'll run out of memory because Erlang, the architectural decision in the Erlang VM is that if you run out of memory, we'll just blow up. There's no sensible way that you can recover from an out-of-memory condition in all cases, so we won't try to do it in any cases. Just don't run out of memory. It's a much better way to do it.
So can you ask the VM if it's getting close to running out of memory?
Yep, that's coming up in the monitoring section. Also bad. Perhaps a little more subtle here, but this is kind of a nice naive way of counting the number of times a loop's been run. So each time we loop into the loop function, we add 1 here, and as the last, we add 1 to the return value, and the last time it runs, it returns 1, so the return value from all this becomes the number of times the loop was executed. Fine, except it's got to keep this bit of stuff on the stack each time it calls loop. So if this is run 100 billion times, it might be very interesting to know it was run 100 billion times, but you'll probably run out of memory long before that, because this cannot be tail recursed again by the compiler. This is kind of a little bit surprising that it's bad. Erlang has a nice exception system, which is part of its whole robustness thing. We try to call a function. If there's an exception, we catch it, and we're all doomed, but we'll deal with it. If it returns continue, we loop again. If it returns done, we return OK. That looks like it should be tail recursive, because foo is the last thing we do, and we loop back. But the problem with this try catch block is it says catch anything in this whole section here, and that includes any exceptions thrown by foo. So it's got to again maintain the stack so that it knows to catch out here, and every time you loop, it's building up another layer of try catch. And so this is not tail. This whole thing rather is not tail recursive, and again it will blow up your stack if you let it run too long. This is how to solve it. The Erlang people in their infinite wisdom have introduced try of. It looks almost exactly the same, except the only bit whose exceptions are caught is f of x here. As soon as you hit the of, it is no longer catching exceptions, and you can do foo, and that will tail recurse safely. So that's tail recursion and how to blow up the stack if you're not careful. Message queue overflow. Message queues are simple and really powerful and awesome, and get you into really deep trouble. There's two basic ways to get into trouble. One is just outright overload. Bunch of processes throwing way too many messages into one process's message queue. It's too slow to handle them all. That queue will just grow and grow and grow and grow and grow. And again, the lack of out-of-memory protection means it will grow and grow and grow and grow and grow until you hit your 32-bit 3 gig limit, and your whole machine will segfault, and you'll have 8,000 unhappy customers again. The second one, which is a little more subtle, is selective receive. So I'll talk about each of these. The most common way people seem to get into trouble with outright overload, judging by the mailing list and our own experience, is doing what seems like a really obvious thing, and having a process that manages the log, and have all your processes feed in messages to this saying, I want this message logged, I want this message logged, I want this message logged. And as a simple solution, it's quite nice. The problem is, if you have 8,000 phones all throwing lots and lots of log messages at this one process, which is both formatting the string and writing it out to disk, sooner or later, this is going to fall behind. And as it falls behind, its queue is going to grow and grow and grow. And I've seen more than one person on the mailing list, and indeed our own experience, going, why did this run out of memory and crash? I don't get it. And it's come back to a function almost exactly like this, where they've written a central logger process, have everything piling the messages onto the queue, that message queue grows and runs out of memory. The solution to this, or a solution to this I should say, which I haven't actually written up on the slide, but is to have this log message function at this point wait for a message back from the logger process. So we format and write, and then we send a message back to the sender, and each process doing the logging then is not allowed to proceed until it knows its message has been logged. That slows down all the other processes, obviously, but the thing is, it only slows them down enough. It slows them down just enough to make sure the logger process doesn't get overloaded. And even if you have 5,000 processes all writing, even if you have 5,000 processes all writing, that queue will grow to 5,000, but that's no big deal. It will get through them, and yes, stuff will slow down, but it will slow down only as much as required, yeah.
Do you have a construct like a buffered receive message?
No. I mean, you can build your own, certainly, but the built-in Erlang message queue stuff is dumb, for want of a better word. Yeah, you certainly could, but yeah.
Receive things in it, but only send a message back.
Yes, of course you could, but this is the built-in way of passing messages around, and you can pretty much make this work with a lot less effort than rewriting the whole thing, which has already been nicely written for you to work for. Yeah.
If you're building in the queuing system to do processing, maybe you are processing thumbnails or whatever you're doing, and you had a log like this, you'd have a monitor that would actually sit there and say, queue's getting larger, I'll just spin up another process or even another machine to handle that. Couldn't you do the same thing for the logger?
Yeah, you could. That's certainly another solution, is load sharing and stuff. I mean, the thing with the log is ultimately it will probably, the thing that's most likely to block it is the writing to disk. And if you spin up another process that's also trying to write to that same file, that's not actually going to improve anything. But yeah, so certainly you can monitor things, and if the problem is conducive to being parallelized, sure, parallelize away, because that's what Erlang's really great at. Selective receive. So this is where it gets a little bit more subtle. The receive keyword has a way of only looking for particular messages on the queue. So it's not, the message queue is not a strict FIFO. You can actually say, I want to block until I receive this message, even if there's other stuff in the queue. I only want to continue once I see this message. And this is really good for if you've got a server process that, rather than just doing a request response, needs to have a bit of a conversation with a process before it goes on to serving another process. So request, response, request to, response to, and you can look for only that request to, and other requests can build up in your queue and you'll still only get that, which is cool, except that the way it has to do it is, as soon as it does that selective receive for a particular message, that operation becomes order n in terms of complexity, where n is the current length of the queue at the time receive was called, which is fine when you've got a lightly loaded process. But if you hit that selective receive and you've already got 10,000 messages in the queue, it's got to scan that entire message queue to see if any of the current messages there are a particular message. And that becomes a very expensive operation. And if you've got a heavily loaded process that's doing that, every time you hit it, it's a very expensive operation, and probably you've got other stuff building up even more of a queue. So the next time you hit it, the queue will be even longer, and that will take even longer. And you can see how that becomes fairly explosive fairly quickly. Compare that to a normal receive where you are happy to pull anything off the queue. That's just order one. That just grabs the first thing off the queue, and that is completely independent in terms of cost of the length of the queue. So okay, that looks like it should be reasonably easy to avoid, or at least keep to only situations where you know it's going to be a lightly loaded process. Except it's not always obvious where it's going to happen. If you're using Amnesia, which is the built-in in-RAM database system, which is really cool, by the way, that's another couple of talks on its own. The Amnesia transaction operation, which is just looks to you just like a relatively simple library call, it actually has a selective receive in it. And this isn't documented, you know, in keeping with the rest of the documentation. They don't particularly mention that kind of thing. But that can suddenly, that relatively harmless looking function can get you into a lot of trouble again if you've got it in a very busy process. And that was in fact one of the problems we get. We're like, man, why is this process suddenly going really slow? There's no selective receives in it. Dig into the source code for Amnesia. Oh wait, yes there is. Dang. The thing is, even queues going to take hours or even days to actually crash your system. And this is where monitoring becomes important again. Because you're dealing with potentially, this queue probably has to grow to 2 gig or something before you hit a memory limit on a 32-bit machine. And you've got plenty of time to deal with it. And the nice thing about a runtime environment like Erlang is you can actually dive into a running system and do whatever needs to be done to fix it before it actually causes a problem for users, which is cool. This selective receive thing is also somewhat mitigated as of release 14 of Erlang with new reference optimization, which I'll talk very quickly about. This makeref function here is a built-in Erlang operation that gives you a guaranteed unique reference, or guaranteed unique enough, it'll repeat after 4 billion times or something, but good enough for government work. You send the server a request with that reference in it, and then do a selective receive for a response with that reference in it. The compiler is now smart enough to say, well, at this point I'm doing a selective receive, but I know I'm looking only for something with a reference in it, and that reference was only created there. So anything that was in the queue at this point, just before makeref, cannot possibly be included in that selective receive. So I don't have to look at anything that was in the queue at that point. And if you've got 100,000 items in the queue at this point, it only has to look at everything that was added to the queue after this. So that makes it a lot faster and a lot better, but doesn't solve the amnesia case and probably doesn't solve a couple of other internal cases that we haven't encountered yet. But that's a neat little bit of compiler trickery. Next thing, Erlang as a Unix service. Erlang comes from an embedded background. The sort of flagship use of Erlang from Ericsson's point of view, Ericsson being the company that actually developed Erlang in the first place, is this AXD301 switch, which is a very nice bit of kit. Claims insane uptimes in part due to hot code loading and stuff. But it's an embedded device. You turn on the device and you walk away. It's not a server in and of itself. And that's the environment in which Erlang was developed and kind of grew up, if you like. But in the Unix world, that's kind of not how you want services like Apache to operate. You want to be able to start them, to stop them, to check on their status, to do upgrades and so forth. So your usual startup of Erlang will look of an Erlang server will look something like this. You'll call Erl no shell because we don't want it to be interactive. Detached says immediately detach from the console and don't continue logging to output. I want my shell. Boot up my app, which is cool and simple and always returns 0. Success, hurrah, happy sysadmins. Except it even returns 0 when everything goes wrong and it fails dismally and crashes a second later. Also, detached says detach immediately from the console. Don't give me any output. And there's no way built into Erlang to defer that detachment. So a sysadmin it's like 2 in the morning, they've come in to restart the thing. They go restart, bang, it returns 0, produces no output. They're like, great, I can go back to bed. And they come in at 9 in the morning and everyone's like, why the hell is the system broken? It's because they started it up and it didn't actually start up properly, but there's no feedback, and that makes them unhappy. Another thing that you're probably used to if you've been running Linux or Unix services is the generation of PID files so that you can actually locate the process which is running a particular service. And they're a really useful little thing. You can find out which process to kill if everything locks or gets into an infinite loop or whatever. They're also used by things like RPM and deb to manage upgrades, to find out which process to stop or kill. They're used by init scripts. If you do a restart and it can't restart it nicely, it will eventually probably do a kill-9 on whatever the PID is. And Erlang has no nice built-in way to the emulator to generate those. The native solution, of course, is just, well, as the first thing I do in my code, I'll just write out my current PID to a file, and everyone's happy. But what if your code never runs? In Erlang, there's an awful lot of stuff that goes on in terms of loading libraries and everything else before you even get to executing your code. And it's those cases where it gets into some kind of crashy, loopy thing before your code even runs that the PID file is the most valuable, because that's when you want to find that server and kill it. So that solution is not going to really work for us. Heart is a built-in system to... I will get to how we solve this, by the way. I'm just running through the problems that we have to solve to run Erlang as a service. Heart is a great little idea for embedded systems. It spawns as a parallel process to the Erlang VM, and it watches the Erlang VM. And if the Erlang VM crashes, it restarts it. It's a watchdog, and it in turn is watched by the Erlang VM. So if, God forbid, this little Heart process crashes, the Erlang VM will restart it. So you've got 2 processes monitoring each other. which is very nice. The problem is, if you actually, again, get your code into a horrible loopy thing where you can't kill it, if you kill your, where you can't use it, sorry, you call kill on your early process, sorry, not early, you call kill on your Erlang VM process, and Heart will go, oh, it's died, I'll restart it. You go, oh, shit, okay, I'll kill Heart first. The Erlang VM goes, oh, Heart's died, I'll restart that. And yeah, you can see where this is going. Kill stop is your friend in this case. It actually stops both the processes, allows you to stop both the processes from running and then executes the kill. But really, there should be a much better way. Heart's great, as I said, for embedded systems where the only sensible behavior, if you turn it on and it gets into a loop, is to just keep trying. And, you know, maybe send someone in with a debugging console, but that's not really, an embedded system is supposed to turn on and just work. So Heart is fine as the only sensible behavior. There, it's not so good for Unix services. Final thing is log rotation. Erlang's internal implementation of log rotation and its default logger is absolutely nothing like the stuff you're used to in Apache. It actually tries to be smart about managing log names itself and tries to be smart about moving log files. And its smarts, again, while kind of probably good for an embedded system, are absolutely nothing like the de facto standards you're used to from Apache and such like. Where in Apache, if you want to do a log rotate, you send it a SIG hub. Sorry, what you do first is you move the existing log file, it keeps logging to that, to apache.log.1, you send a SIG hub, it closes that file, opens apache.log and continues logging. Great. There's no way in Erlang, in native Erlang code, to actually intercept a SIG hub. So you can't do that in Erlang as it currently stands. And all these quirks put together, the PID files, the logging, everything else, means that it's actually really difficult to use the standard package management stuff to manage your Erlang application, because they rely on part or all of those behaviors to various degrees. And it's also often difficult to run it as a service as your sysadmin is expected to behave like Apache. So our solution to this is a program we've written called LD. If you're familiar with GNU Screen, it's a wrapper for some kind of terminal program which basically manages that program's terminal itself. So if you've got an IRC session running in VChex or something, or Urki or whatever your command console IRC client of choice is, but you also want to be able to throw that into the background. Well, you can't just hit Control-Z because that kind of suspends everything and suspends the network connectivity and stuff. But if you run screen IRC-II, you can then hit Control-AD, it'll throw that into the background, but it'll continue to log the output and continue to manage the console, and you can then bring it back into the foreground. Screen is a really neat little program. And we've used much the same system in LD. We grab the console that the Erlang VM is running on, we hold onto it, but we allow it to be detached from the main console, just like Screen allows. And we allow that to be programmatically tied into a little bit of code in Erlang, so we can start up our Erlang. And once we're happy that everything's started and is running smoothly, then in our Erlang code we can call LD detach, drops you back to the console, returns 0, then the sysadmin can actually know for sure that yes, it's started up, it's running, and all is well. Or alternatively, it allows us to report errors back, to both through error codes and through output. It also, because it continues to run in the background in managing the Erlang VM itself, it allows you to intercept SIG hub and then call your own log rotation function, which behaves in the way that people expect it to. And like Heart, it also manages crashes and restarts, except it does it in a slightly more flexible way, where you can say, look, if it crashes more than 4 times in 5 minutes or something, configurable values, then it's probably not going to work for us, so just shut down the whole thing, send error reports to people, email people, page them, whatever. I'd love it to be open source. I'd love to tell you where to get it. It's not yet, but if anyone is interested in using it, come and talk to me afterwards, because we can arrange things. Is there a question up there?
No, I'm interested in using that.
Okay, cool. Come and talk to me afterwards. Yes?
Is there a plan to open source it?
I have a plan to open source it, and my plan is to convince the company to open source. They're receptive to the idea. It's just you know how companies are. It's a matter of going through all the processes and stuff. Yes. Hot code loading. Hot code loading, as I said before, sounds like a really awesome idea. It promises ridiculous amounts of uptime because all changes to your code can be made without actually bringing down the system at all. depending on who you believe, Ericsson claimed to get 9 nines of uptime on their AXT 301. Though, if you read some of Joe Armstrong's stuff on the matter, he's like, actually, no one's ever done any academic research to back that up. So, but it's probably providing pretty good uptime, regardless. But no one outside Ericsson seems to use it for more than pushing in a single module at a time. Managing a whole release with hot code loading is actually really, really, really hard. RabbitMQ don't do it, yours don't do it, eJabberD don't do it. And it's because it's hard. And unless you're Ericsson and know and are doing this a particular way and know exactly how to do it, it's going to be nigh on impossible for you to do it, to be perfectly honest. There's not a lot of good tools that come with it, that come with Erlang to help you manage this hot code loading stuff. The documentation is patchy and clearly written by people who are already using this stuff in their particular way and haven't given much thought to how the broader community might like to use it. And there's absolutely no thought given to integrating with RPM and stuff, which is a shame because the installation and upgrade of RPMs is intrinsically tied to this. There would be nothing that would be more awesome than grabbing a new set of RPMs, going RPM upgrade my application, and have it hot code load in the new version into the running system with no restart required. That would be so cool, and that is really, really pretty much impossible at the moment, which is a shame. And it's hard to test, because what you've got to do with hot code loading is basically take the running state of each. I'll go back to the phone example. We've got 8,000 phones. You've got to take the running state of each of those phones, transform it into a state that supports the new code. So what actually happens internally is it freezes that for a second, runs a state transform function that you have to write to do the upgrade, and then restarts the code in the new version. And that's really hard to test because there's 8,000 phones in 8,000 different states, and you're probably going to get it wrong in any reasonably complex situation. In any reasonably simple situation where you're just changing the spelling of the word conference, it's great because you're not actually doing any state transforms and stuff. But for big upgrades, it's still really hard. And there's no easy solution for this one, unfortunately. It's all I'm basically trying to say with this slide is be aware that hot code loading, while touted as this great feature of Erlang, and it's true it exists and does work, it's not going to allow you to, not without a huge amount of work, upgrade a massive running system without bringing it down. Yeah.
Is there anything along the lines of a rolling upgrade where as clients disconnect and then reconnect, they connect to the new one, the old one?
You can do it that way, but the general the general way it's run is that the code is actually replaced at some predefined point. Sam can probably talk a little bit more in detail about this after if you're interested, but it's generally done when the code is resting, as it were. You can actually suspend the whole code, transform the state, and bring it back into that resting state, and it will keep running. System monitoring. So how do I know if my system's about to break? The Erlang VM, like the Java VM, has a lot of cool ways to look into the running system to do inspection on it. But that's only useful if you actually use them. And it's only useful if you know what to look for, what problems might actually be occurring. You can look at these 100 different functions that monitor stuff, see a bunch of numbers and go, oh, cool, okay, it looks like it's working fine. Here's a few things that you'll probably want to look at. Straight out number of processes. Erlang, being nicely garbage collected and stuff, doesn't leak memory, generally speaking. There are ways you can make it do it, but for the purpose of this argument, it doesn't leak memory. What it can do is leak processes. You can spawn 8,000 processes and then kind of forget about them, and they just drift off to the side going on their merry way, perhaps not doing anything, but they're still there and they're still consuming resources. Erlang processes, that function, returns the number of returns a list of all the running processes in the system, and length is just an operation that returns the length of the list. So if you just keep an eye on that, on the return value of that, if the load on your system is steady and that number's climbing, you've got a process leak somewhere. And again, the nice thing about this is because you can inspect the processes directly, you can probably track down while it's running without doing any invasive testing where those processes are leaking, and even manually kill them off to keep your system running nicely. And then you can put in a bug fix as required. Queue length, which I talked about before, this is message queue length. The way to watch a process's queue length is to call Erlang process info, pass at the PID of the process, message queue length. And that will just return an integer telling you how many messages are currently in that process's queue. And so what is a really good idea to do, if you've got a few busy processes like a logger, like some central server which does a lot of work, is have another process sitting off to the side, which every 5 seconds or whatever calls that function on those processes. That's an order 1 function, by the way. It just looks directly at the length field in the list. And you can watch those numbers, and if one of them starts to climb and climb and climb and climb, fire off an alert, maybe manual intervention again or something. And again, you can catch the problem before it actually becomes a major problem in terms of a crash or something. And finally, total memory use for the person who asked earlier. There's a function that will get you the total memory use and also the memory use in terms of atoms and strings and heap space and stack space and whichever little bit of information you're interested in. So this is just a very brief sample of the sort of stuff that's required. There are a whole bunch of things that you can monitor. These are some good ones to start with. How am I going for time? Not very much late. Really quickly, the Open Telephony platform is one of these things that's not at all mentioned in any of the Introduction to Erlang tutorials you'll find. And I can see why, because it's not a part of the language per se, but it is like the STL in C++. It's kind of an intrinsic part of the language as a whole ecosystem. It's an architectural framework that allows you to write the robust, big, high-performance programs that Erlang promises on the brochure. It forces you to consider how your processes are laid out in terms of links, failure. If this one crashes, well, what does that actually mean? Do I need to also restart that one? And so on. How many times should I restart this before giving up and deciding that it's an unrecoverable bug in my code? If you're only writing a 2-module, 400-line program, it's going to be overkill. You don't need it. If you're writing anything big, it's absolutely mandatory. Mandatory in the sense that you would be a complete fool not to use it, because it's what gives you those features of Erlang, the robustness. So read up about it. Once you've got past your little hello worlds and your little string processing Erlang programs, if you're writing anything big, learn the OTP before you start, because converting stuff to the OTP later is it's quite doable, but it's a bit of a pain. Yeah.
But if they're into things nothing to do with telephony?
Absolutely. Named thus only because Ericsson is a telephony company and most of the stuff they write is for telephony. Yeah.
Actually, a really good book is Erlang OTP hash.
Yep, cool. There's also for anyone who's really interested in this, there's I believe a Erlang conference up in Brisbane later in December, and there's going to be a 2-day course on the OTP, which I would love to go to, but won't be, unfortunately. So very quickly, the OTP, solving problems you didn't know you had. If you want to make a call to another process, so I have my process here, I have a server process over here, I want to send a request, get a response back. Okay, nice naive little solution to it. I send a server, I take the server process, I send it a request, and I receive a response from it with the response data. Great, looks fine. No problem. Except how do I make sure it's the right response? How do I make sure that there's no other response sitting in my queue or that's been sent erroneously to me or whatever? So we use this little make ref trick that we made earlier. We create a unique reference that applies to this request, we embed it in the request, and we look for it in the response. And this also nicely gives you that new reference optimization I was talking about before. Okay, that's cool, that's only 5 lines, no problem. What if the server process doesn't exist? What if it's briefly crashed and is in the process of restarting but isn't there yet? Okay, so we can use where is Erlang built in to find the server process. And if it returns undefined, that process doesn't exist, we return an error. Otherwise, we get the PID back of it, we do the make ref, we send the PID, we do the receive response. Blah, blah, blah. Okay, it's starting to get a little bit complex, but that's fine, it's still doable. Okay, what if the process dies after we made the call? It existed, we send it a message, but before our message got pulled off the queue and processed, something else crashed it and it's in the process of restarting. That means it will have lost its message queue and our response will be dead. Well, you can time out. You can, in the receive block, you can add, after 5 seconds, some useful timeout, return error timeout, rather than sitting there waiting for a response that will never come and hanging this process indefinitely. That's nice, but waiting 5 seconds if the process crashed, we can see that it crashed. Why would I want to wait 5 seconds for it? Okay, so we use Erlang monitor. We monitor the server process, we get this monitor reference back. And down here, monitor will send us this down message as soon as that process becomes unavailable. So we sit in this receive block waiting for our reference to come back. or for a down message, or for a timeout. And we have to remember to demonitor stuff afterwards. This is starting to get really complex. And what if the remote process doesn't support the monitor interface? You can write processes, Erlang-style processes that look like processes to Erlang in C and Java and a couple of other languages that have bindings, but they don't support the monitor interface. Okay, so there's ways to get around that too, but this is getting kind of silly for what should just have been a simple call. The OTP gives you this. It's written by people much smarter than me who have thought of all these possibilities, have lots of code that handles it all, and expose it to you in this simple API call. The trade-off is you've got to make your server process look like, implement the gen server interface, which isn't nearly as bad as it sounds, and it actually makes for some, it makes you think about how you're implementing it, and it makes everything have a nice common interface that solves all these problems before you even think about having them. One of my colleagues encountered this when he sent me some, relative newcomer to Erlang, sent me some code and go, right, so I think I've covered every single one of these cases and I've got this, and I'm like, yeah, that's great, that's exactly what you should have done, and it's all done for you by this. So, nice work, but someone already thought of it. The OTP does other stuff. It manages the supervision trees, so you have all your processes structured in supervision trees. You can use a nice little graphical viewer called Atmon to look at them in real time, click on them, find out what they're doing, get all sorts of cool feedback. When one crashes, if it's intrinsically linked to some peer processes, you can cause them to automatically crash as well, restart the whole thing and bring it back to a nice known state. It's got built-in event handlers, so you can very easily implement a subscribe notify type system. It's got FSMs. It's got a whole bunch of cool stuff, all of which you can absolutely implement without the OTP, but you'll just be reinventing the wheel. You should use it. I've added the dialyzer slide in the wrong place. Very last thing I want to talk about in the last 2 minutes is dialyzer. Erlang, for those of you who are familiar with it, you'll know it's a dynamically typed language. You don't have to declare anything as an int. You don't have to declare it as a list. It just infers it. Your variables can, depending on the running situation, can be a list or an integer or whatever. The first time through, that could be an integer. The second time through, that same variable could be a list. And it allows you to write really flexible, really simple code. It allows for great refactoring opportunities, because if you have a variable that's an int up here, and it goes through 3 functions, and then it's used down here, and you decide you want it to be a string, not an int, you don't have to change any of those intermediate functions. The signatures remain exactly the same because there is no type built into the signature. It also allows you to write code that's just flat out wrong that the compiler will never find. You declare something as an int, and then 3 functions down you use it only as a string. It'll crash, but it'll only crash at runtime, which is a really bad time to find out that your code is wrong. Dialyzer is kind of, it effectively gives you a lot of the static type checking that you expect from C and C++, but on the dynamically typed language. And the way it does this is it looks at everywhere variables are assigned and goes, okay, for any possible code flow through this, it could be an integer or a string. And then it basically draws out this massive tree of where every possible variable can end up, and where every possible variable can be used, and how it can be used, and what type it's expected to be when it's used, and tell you when this int up here is being used as a string down here. It's not perfect, and there's some stuff that you can do, including function specs and stuff, to give it hints about what it should be doing. And it can't track variable passing through messages. So there's a couple of tricks you can do to mitigate that. But fundamentally, if you pass an int to a message that's doing a receive on a string, Dialyzer can't find that for you. But it can find an awful lot of stuff. And you'll be surprised how much stuff it finds in your code the very first time you run it. I will absolutely guarantee that for any non-trivial program you write, the first time you're in Dialyzer, it will find a bunch of bugs. Maybe bugs that were never going to happen, but bugs that could happen.
I think that's very specific to Erlang, because we've got a lot of other languages.
Dialyzer is absolutely specific to Erlang. The broad concept is certainly broadly applicable, but Dialyzer itself is only useful for Erlang. The catch with it, Erlang compiles very quickly because it's dynamically typed, in part because it's dynamically typed. Dialyzer on any decent-sized thing takes many minutes at a time to run, but you can add it to your check-in process or whatever, so you don't have to waste that time, and you'll still get the feedback. Oops. So, take-home messages. Understand tail calls, keep your message queues short, or if you can't keep them short, at least understand where the big ones are and make very, very sure you're not doing selective receives on them. Erlang doesn't work out of the box as a Unix service. You're going to have to do something to make that happen. Hot code loading can work, but not on a big scale, unfortunately, yet. Monitor your system like a hawk. There's all sorts of things that you can detect before they cause problems for anyone with relative ease. Use the OTP, use Dialyzer. That's all. Do we have time for questions?
Yeah, lots of questions.
Yeah. Anyone? Yeah.
Is there anything you can over like Dialyzer that will tell you that your functions aren't being tailed recursive, so you can keep an eye for that?
Good question. Not that I'm aware of. Yeah, Sam.
We've been considering writing an extension proposal. Erlang has an area sort of quite open in the development of Erlang, and I'll take proposals about language changes. And we've been thinking about writing a proposal to somehow tag tail call in source. So you tell the compiler this should be a tail call, and they'll throw a compile error if it's not.
Yeah.
I guess you agree with that. Yeah, that's a good thing to see.
Yeah. Unfortunately, no, there isn't at the moment. Yes.
Is it good for multi-core use? Like, that's
It's brilliant for multi-core use because what it does is the VM itself looks at how many cores your system has and will start up exactly that many OS threads, and then it will share its lightweight threading and stuff across that. So yeah, it works really well. And beyond that, it's actually Erlang's got some fantastic clustering features as well. You can treat a process on a remote node exactly the same as you treat a process on a local node. Obviously, you've got to be aware of the possibility of network failure and all that. You know, it's not some magic wonderland where stuff on the other side of the world is exactly the same as stuff here, but it is as transparent as I've ever seen any language in terms of clustering.
There is a bit of a caveat there that multi-core support is relatively new in Erlang. So the current versions are quite good and they're improving it, but there have been some problems with global lock things holding up performance on XMPs sometimes. Yeah. So basically, that's a core aim of their focus. It's very good multi-core support. So where it's not ideal, they're certainly working hard on it.
Yeah, there's an EU proposal for research. There's a research project that been started on multi-core. Yeah.
Cool. I'm not. Nice. Yeah.
Have you tried Rebar and the stuff from?
Yes. I was going to mention that, but I didn't really have much time to. Rebar is really good for what it's really good for, which is a certain subset of uses of Erlang. And in the simple case, it will allow you to compile and distribute your code really easily and really quickly. And it's got a lot of limitations that mean, unfortunately, it's not very useful for us. We've certainly looked at it and spent. I mean, again, Sam was the one who did most of the looking at it, but the general conclusion was, yeah, it's good for this subset of stuff, which actually covers a lot of people's use, but not ours. Anyone else? All right, thanks very much.
Here's a present for us.